Okay, let's summarize this kernel track a little bit. And I'm going to tell you and also what kind of kernel that we should be choosing here. So this is summary, the kernel trick. So we're given a data set. That is, for example, is the x of I, y of I, right, from 1 to n. So these are a bunch of training data. And we pick a kernel. So we don't actually choose this phi in general. We just choose the kernel directly. So there are multiple choices of kernel that you can and make choices right here. For example, you can choose the linear kernel. So that corresponding to the linear features. This just being like inner product. That would be x z transpose if we think and sorry, I'm using the column here, so this will be x transpose z. Can take the polynomial kernel. So you can, and you have to specify the degrees. It's all polynomial up to degree of d k. So with that, this will be k x of z equal to x is 1 plus x transpose of z power of k. Okay, I already show you the situation when k equal to 2. But this also, I mean, this whole formula will work even with like other degree of k. So this is and include all the polynomial up to the degree of k. So that means if k is 5, that means I'm going to consider degree of 0, degree 1, degree 2, degree 3, degree 4, degree 5. Another popular one is called Gaussian kernel. So I have a kernel right here, looks like exponential minus x minus z divided by 2 sigma squared. And this is sigma here. So basically, this is a Gaussian and the distributions. For sigma is bigger than 0 right here. This corresponding to some infinite dimensional feature spaces. So that, I mean, this is quite special. This P is actually infinity. There's no way that you can like directly work on the phi. So this is something that is very special here. You cannot choose kernel arbitrarily. I mean, we don't need to know what kind of corresponding phi. I mean, it is explicitly, but it has to exist. So that means, so this kernel has to satisfy some conditions. So kernel K has to satisfy some and some conditions to be a kernel. So this is called Mercer conditions. So what does that actually means? So, and so the Mercer condition states if for any data we have x1 to x of n in R small d, then our kernel matrix K ij is basically K of x of I and xj is positive semi-definite matrix. It's always a positive semi-definite matrix. Then this kernel is a kernel functions. Right? So this is very important. So that means for kernel matrix, this matrix has to be positive semi-definite. I mean, if it is not positive semi-definite, this is not a kernel function. So we cannot choose arbitrary functions of RD to RD and RD times RD into R. So you have to choose specific kernels, has some specific values to ensure if we plug in the xi and xj, this whole matrix is always positive semi-definite. Okay. So and let's go back. So and given a data set, we pick a kernel. It can be arbitrary kernel as far as this Kij. If we plug in xi and xj, this matrix is positive semi-definite. So so what we do is we think about, you can pick a choice for some loss function. We are going to use some linear predictor of the form. So my W hat, which is my optimal W, you can think about as a linear combination of my alpha I of phi x of I transpose. So this is basically a linear predictors with and with phi is my features right here. So for some alpha here, so alpha here is alpha 1 to alpha n. It's in Rn. This is to be learned. And here we assume this form is and this is like linear predictor form. Okay, so the whole idea is we design an algorithm to find alpha just using kernel matrix. That means we only use phi of xi and phi of xj as a whole pair together. We don't use phi x of I separately. We only use the phi xi and the phi xj transpose separately. So sorry, the I'm as a pair. So they only shows as a pair. So this is how we do the training. So this is the training part. And then the next prediction part. The prediction part is for new data. X is Y equal to phi X times W hat. Right, so this is basically we just plugging this. Then we're getting summation of 1 to the n alpha I phi X and the phi X of I transpose. Okay, so this is actually can be written as K of X, which is a vector right here, and the inner product with alpha. I think you choose alpha to be I think I choose alpha to be a column, so I don't need to transpose it. So this is row, this is a column. Okay. In terms of the ridge regression, so this is a general an idea, and of course we need to still pick the loss function right here. If we just happen to pick the ridge regression loss, if my loss function is precisely the ridge loss, so again it's arguing. So we sum of I from 1 to the n, I phi of X of I W plus lambda of W. Right, so this is basically the loss function that we're interested in. So then this becomes, and we're going to plug in this W because that's the thing that, and we need to translate, right? So we're going to translate this into, I want to find out alpha hat. This becomes argument. Instead of we work on the W, but we know W has the form of this. So that means this becomes summation of I from 1 to the n yi minus summation j from 1 to the n again, alpha j phi X of I phi of xj transpose. Right here, okay? Then you put the square root of 2 norm plus lambda. So you have alpha like it, and you're going to substitute w by the alpha. So this is double sum of alpha I, alpha j, phi of x I, phi of xj, transpose. Okay, so we can write everything in terms of vectorized. So this is not arguing with the w, this becomes arguing of alpha. So this is become arguing of alpha. Y minus, I'm going to write as a matrix form with k and alpha. And we think about an alpha being a column right here. This is square right here, plus lambda alpha transpose k alpha. So this is all write everything in terms of vector form. Then this becomes and ridge regression in terms of in terms of alpha now. So we can take partial derivative with respect to alpha right here. So this becomes, I believe it's K transpose of y minus K alpha right here. Oh, I'm going to do it this way, K alpha minus y plus 2 K alpha here. Then I have a 2 here. If we assign this equal to 0, wait. I see. That's right. So, this is equal to 0, but K is positive semi-definite matrix. So this is actually, and whether transpose or not doesn't matter. We can get rid of the transpose. So we can factor out this 2K here. This is K alpha minus y plus oh, I missed lambda here. And the lambda alpha here equal to 0, because we know K here is always positive. And not only, and I hope if K is positive definite, then I only need to solve this whole thing inside is equal to 0. So that implies I have K plus lambda of identity of n by n of alpha equal to y. That indicate y hat is equal to K plus lambda of n by n inverse of y. Okay, so this is if we happen to choose our and objective functions to be the same as the ridge regressions. Okay, but you can think about everything right here. It's still up to and determine if we change a different loss functions. If we have a generic loss functions, and we can at least try to do is we can using gradient descent to find this situation right here. So the most general cases, so if we have a feature map of phi x, so what we want to solve is W hat is argue mean W, a summation of I from 1 to the n. It's a loss function. It's a generic loss functions of phi of xi times W and the y of I. For some convex loss. So this is some convex loss functions. And for the gradient descent update, we can find the optimal solutions as follows. And we can use gradient descent algorithm. And you can starting from some initialization of W0 is from the 0 vectors to make and to work on and the gradient descent. So that means and I can update t plus 1 from t and subtract to and going along this gradient and the directions. This is from 1 to the n L prime and don't forget I have this partial derivative with respect to W here. So I have one term coming from phi L xi transpose. So the key here is all this whole thing, I mean WT, lies in the on the subspace spanned by phi of xy. So the reason you can think about right here is these are actually a scalar, right? So these are actually the vector. So it's a scalar multiply a vector, you sum them together. So that means everything that we're trying to do is we're subtracting a vector that is spanned by phi of xi, which in this case is n-dimensional. So like basically this subspace right here is n-dimensional. So we can think about this as actually an n-dimensional subspaces, but this whole thing is actually lives in RP. So you can think about we are working with n and the subspaces in RP, but the dimension is only n. So that's why this is really important. This is a very key observation that we can simplify our calculation significantly. So that means we only need to consider the solution represented by the phi of xi. So that means this is always in the span of phi of xi. This subspaces embedded in RP. So that's why this whole idea is really efficient. So this kernel trick, actually, we want to find these optimal solutions by searching over all the models that can be represent my W hat in this ways. All we need to do is to find out this optimal alpha instead of optimal W here, because W hat lives in much higher dimensions, but my alpha here just lives in the dimension of n, so which is significantly smaller. So you can see this is the whole idea of general cases why the kernel trick will work. This is only makes sense if we have and the feature space is significantly larger than the and the number of data of n right here. So in the rest of the lecture, we're going to talk about a very specific kernel right here. It's called Gaussian kernel right here. You will see this kind of kernels in the later of the courses in much detailed way. You can see, and this is the and a Gaussian kernel, and this Gaussian kernel also has a name called radial basis functions, because what we care is just a square of Euclidean distance between these 2 points. So you can think about if we have a bunch of examples of x and y's right here for n, endpoint right here. So what we do is we create this kind of basis functions. So this is my basis Gaussian, and the Gaussian basis right here with the bandwidth of the sigma. So like sigma here is, you can think about one standard like deviation here. So we create all bunch of functions here with these like similar same Gaussian and the Gaussian basis functions. Then the function that I want to approximate is basically linear combinations of these Gaussian functions. Each Gaussian functions in terms of in R, that will be infinite dimensional because this is an infinite dimensional object. But here we are summing the finite number of and the Gaussian functions to represent a functions. So that's why this whole function will be infinitely smooth, but still a finite dimension if we consider the basis of the Gaussian and the Gaussian like radial basis functions. So if we think everything in terms of different bases, I mean, these functions actually live in finite dimensional and like subspaces. So that's how we think about and everything in terms of the kernel traits. So basically, and we can using like all different ways. So and this predictor is basically taking the weighted sum of this n kernel functions centered at like each example point. And we can tune different bandwidth and tune different like lambda as well. And you can see if we choose a very small bandwidth, so that means you can see it's almost like and a big spike. I mean, it's almost like delta functions. And you can see if we choose like sigma, the bandwidth is getting larger and larger up to like 0.1. You can see it can fit the true functions very well. And also we can change our lambda right here. So I mean, and our lambda right here, I believe it's the penalty here. I mean, yes, if penalty is very and small, then like it tends to like overfit. If the penalty is like it's median and it can fit things like really well in these cases. And also right here, if my and sigma is like and 10 to the minus 0, which is 1 right here, so that means my bandwidth is way too large for this type of problems. Then in this cases, my bandwidth and it doesn't reflect and it cannot approximate this function well. So that means you actually need to tune the bandwidth to make sure it can fit the function well. The last thing I want to talk about, which is very close to the homework problems, is when the n is very, very large. In this case, is 60,000 and n-ness data set. In fact, we're using something that is slightly different. That means if n is very large, it's even like allocate n by n matrix will be tough. 60,000 by 60,000 matrix, that's way too expensive to calculate. Instead, what we do is we generate a bunch of random feature maps of this kind of form. So basically, right here, we are creating a bunch of like random features of cosine of xw1 plus b1. And this w right here, they are all Gaussian distributions. It's like and Gaussian IID random vectors. B is the uniform and random vectors from 0 to pi. In these cases, in fact, P right here, P2 right here is significantly smaller than N, and N is significantly smaller than P. Right here, this P right here, and P2 right here, I think we choose about like a couple thousands. That will be significantly smaller than N. In fact, we can show if we take this random feature map, it can be effectively doing this and Gaussian kernels on this data set. So basically equivalently to say, if we are working with and Gaussian kernels, that probably can give us very good result. But the price that we need to pay is we need to work with n by n matrix. But in this case, my n by n matrix is way too large to work with. So what we do is we taking this random feature maps and work with, this random features. It turns out it will be almost equivalent to work with and kernel tricks. So this is the beauty of everything by taking advantage of these random features. In the next homework, you actually, is going to prove this factor. So this is very important factors, and it can be shown, and it can demonstrate the effectiveness of taking these random features. Okay, so this is something additional to this kernel trick, that we're using something called random features to further reduce the and computational cost and to make everything very efficient. Okay, so that's everything.